All right, hello 1020 class. This is test 3 review, which is, remember, Thursday of next week. So I'm not sure if we're going to have enough time to do the entire review today. We might just do, or at least on this video, we might just do half of them. We'll see. But let's start off with number 1 on the review. This is kind of like number 21 from section 4.1 in the book. It says, suppose the graph of y equals x to the 3 halves is shifted down, or let's see, is stretched by a factor of 3 and then shifted up 5 units. So stretched by a factor of 3 and then shifted up 5. All right. What is the equation that gives the new graph? Okay. Well, notice that it's kind of implied that that's a vertical stretching. So the very first step would give us 3 times x to the 3 halves. Because whenever you want to stretch a function vertically, you multiply it by a number that is bigger than 1, in this case 3. And then we're supposed to move it up 5. So after that, all you're supposed to do is just add 5 to it. So 3x to the 3 halves plus 5 should be the answer. So we're supposed to do these two transformations in that order. Okay, so number 2 on the review is kind of like number 33 from section 4.1. It says, determine visually whether each of the graphs is symmetric about the x-axis, the y-axis, or neither. If the graph represents a function, determine whether it is even or odd. Well, let me sketch it for you roughly. Kind of looks like that. So notice that if you reflect it with respect to the y-axis, you get back the same graph. So it is symmetric to the y-axis. No real work to do there. If we try to flip it over, we get a different graph. So it's not symmetric to the x-axis. And if we rotate it 180 degrees, we would get a different graph, so it is not symmetric to the origin. It is only symmetric to the y-axis. And you might remember, if it is symmetric to the y-axis, that is an even function. And it is a function, because it does pass the vertical line test. So it is an even function. Every function that is symmetric to the y-axis is even, just like the basic one, x squared. So remember, that's why we call them even functions, because anytime you raise x to an even power, you get an even function. It is symmetric to the y-axis. All right. We'll probably just do the first 10 on this first video. Well, let's try number 3, which is really number 41 in the book. It says, determine algebraically whether the graph of the given equation is symmetric with respect to the x-axis, y-axis, or origin. And 41 is x cubed minus x, which is really number 3 on the review. So let's just review how to do all the different tests for symmetry. So let's start with the x-axis. Remember, the trick is to replace y with negative y and see if you get back the same equation. Oh, we have a little moth there. Hello, moth. Goodbye, Mr. Moth. All right, so let's replace y with negative y. And try to make it look like the original equation. Well, the only thing I could do is multiply both sides by negative 1. But notice that that's going to change the original function. So there's nothing I can do to make it look like the original equation. So this one does not pass the test for symmetry with respect to the x-axis. But let's try y-axis. And remember, the trick is to replace the opposite variable with its negative, in this case x. And it would probably be a good idea if you put that negative x in parentheses, because you're going to be cubing it in the first term. Well, remember, whenever you raise negative 1 to an odd power, it stays negative, so that first term is actually negative x cubed. And in the second term, it looks like the negatives cancel out, so we get negative x cubed plus x again. And there's nothing I can do there to make it look like the original equation, so it looks like that one is also a no. It does not pass the test for symmetry with respect to the y-axis either. Well, let's try origin symmetry, see if it passes that test. And in this case, the trick is to replace x and y with their negatives and see if you get back the same equation. Make sure you put that negative x in parentheses. So this is the equation that we get this time. And once again, if I raise negative x to the third power, that's negative x cubed. And the two negatives cancel on the second term. Well, notice that I could multiply both sides by -1 here. And notice that we actually do get the original equation back. So this one does pass the test for symmetry with respect to the origin. All right. So the only kind of symmetry that it does have is symmetry with respect to the origin. And if we do check it with a calculator, you can. That's kind of optional, I suppose. Well, it's not perfect, but it looks like if you rotate this thing 180 degrees with respect to the origin, you will get back the original picture. So the picture is consistent with our algebra, that it is symmetric to the origin. Well, let's move on to the next one, which is number 4 on the review, which is really number 47 in the book. Determine whether the function is even, odd, or neither, and it's the absolute value of x minus 5. Okay. So remember, the trick is to replace x with negative x. And if you get back the original function, it's even. If you replace x with negative x and get back the negative of the original function, it's odd. So let's see. In this case, if I replace x with negative x, I get this. But the absolute value of negative x is just the absolute value of x. So it looks like that is the original function. So this one is even. All right. Now I'm kind of using a property there of absolute values. If you take the absolute value of a product, like a times b, you can show that's the absolute value of the first one times the absolute value of the second one. So if we're looking for the absolute value of negative x, that's really the same thing as the absolute value of -1 times the absolute value of x, and that's clearly just the absolute value of x. So in this case, we got back the original function even. Number 5 is really number 53 from that same section. Determine whether each of the complete graphs represents a function that is even, odd, or neither. So this one is either going to be even, odd, or neither. I'll do my best to sketch it. Well, notice that once again, this is symmetric to the y-axis, because if I reflect it left to right, I get back the same picture. So any function that is symmetric to the y-axis is an even function. So always think of x squared if you forget what an even function looks like. That's symmetric to the y-axis. So this one is too. Number 6 from the review is really number 3 from section 4.2. And on this one, we're supposed to review the notation for the sum, difference, product, and quotient of two functions. And this one is number 3. It looks like the functions are x squared minus 2x and 1 plus x. Okay. So on the test, I'm not going to tell you what this notation means, but when you see f plus g of x, obviously I can't. I'm not going to be there. But remember, by definition, this is f of x plus g of x. That's the definition of that notation. You're not distributing the x. It's just notation for the sum of the two functions. So all you really have to do is add them together and combine like terms. The only like terms there are negative 2x and x. And if you see this notation, you're supposed to know that that means the difference of the two functions, f of x minus g of x. So the only trick here is to make sure that you put your g in parentheses, because you're going to be distributing that negative sign. So x squared minus 2x minus, in parentheses, 1 plus x. So again, your actual test might be a little bit shorter. I'm not sure yet. We'll see. I'll try to give you something that you can do in 75 minutes, as usual. So it looks like if you combine terms, negative 2x minus x is negative 3x. And notice I distributed the negative sign first. Next on the list, f times g of x. So you see that closed dot? That's not composition, that's multiplication. So by definition, that's f of x times g of x. And that's just x squared minus 2x times 1 plus x. So it looks like this guy we're going to have to FOIL. The first is x squared, outer is x cubed, inner is minus 2x, and last is minus 2x squared. So I'm going to put my highest power first, x cubed, and then minus x squared, and then minus 2x. That's what it looks like it combines to. So again, sometimes I go a little fast on these videos, but the videos are long enough as they are. So if you have to pause, that's fine, or rewind. And actually, that's a minus 2x. That is minus 2x squared. Okay. Just checking my work. Okay. Well, let's do the next part, f over g of x. So this one has multiple parts to it. So you're supposed to know that is notation for f of x divided by g of x. So in this case, it looks like x squared minus 2x divided by 1 plus x. Not a whole lot you can do to simplify that. So that's the answer. And the very last part says find the domain of f over g. So I'm looking for the domain of this thing. I mean, you can factor an x out of the top, but it's not going to allow you to cancel anything out. So remember, for the domain, if you have something on the bottom, make sure it is not 0. Otherwise, you're going to be dividing by 0, and you can't do that. So the only restriction on x is that it cannot be -1. Just solve this thing like you solve an equation, subtract 1 from both sides. So this is probably one of the acceptable answer choices, but if they force you to put it in interval notation, it's everything to the left of -1 or everything to the right of -1. It's just not -1 itself. That's why I used a parenthesis next to the -1. So that would be interval notation, but that's the answer right there. And I think that's one of the answer choices. So almost done with the first half. Number 7 is next. That was a long problem. Looks like this one is actually number 7 from 4-2. I think I'm going to skip that one. It's very similar to the one we just did. It has a square root in it. The only thing you have to kind of watch out for is if you do have a square root expression, just make sure that it's always, the expression under the square root is always bigger than or equal to 0. But 7 is too similar to the one we just did, so I'm going to skip it. This next one is kind of like number 11. 2x minus 6 is f of x. And 3x minus 1 is g. Okay. So this one says find f of g and also g of f. So those are usually two different functions, remember. And the formal way of saying that is the composition operation is not commutative. But let's start with f of g. And remember, the difference between the product and this composition is the open circle. It does not mean multiplication. It means function f evaluated at g of x. So always do the one on the right first, which is the g. That's 3x minus 1. And then just plug that into the f function. So I'm just going to pick up the 3x minus 1 and I'm going to put it right there where the x is. So instead of writing an x, I'm going to write a 3x minus 1. All right. So now we'll simplify a little bit, distribute the 2, and I get 6x minus 8. So let's go in the other direction now. G of f of x. So once again, work on the function on the right first. And the f is 2x minus 6. So now we'll pick that up and plug it into the g function right there. So instead of writing 3x minus 1, I'm going to write 2x minus 6 minus 1. So that looks like 6x minus 18 minus 1. That's 6x minus 19. So hopefully that's clear. I did a little fast again, but just use your pause button. It's one good thing about a video. And they don't get much easier than that. They're both linear functions. So just checking myself. But all right, well, let's move on to the next one, number 9. Just 2 left on this video. So which one is this? Let's see. This is actually number 21 from that same section. And this time they give us the 2 functions, f of x and g of x, and they ask us to evaluate a composition, but it's a composition at a particular x value. So f of x is equal to 2x squared. G of x is x minus 5 all over 3. And the first part is f of g of 2. But fortunately, you could pretty much do this the exact same way that we just did the other ones. By definition, that's f of g of 2 without the open circle. And always do the one on the right first. Do the g of 2 first. So all that means is plug in 2 right there where you see that x. So 2 minus 5 all over 3. But 2 minus 5 is negative 3. So it looks to me like we're actually finding f of negative 1. All right. So just plug in negative 1 for x into the f function. Get my wire out of the way. And that's really just 2 times 1, which is 2. So part B, this time we're looking for g of f of negative 2. So again, do the one on the right first. F is 2x squared. So if I plug in negative 2 into that function, I get 2 times negative 2 squared. And that's g of 2 times 4, which is g of 8. So what is g of 8? We'll just plug in 8 right there. 8 minus 5 all over 3. And that is 1. So hopefully that's clear. Notice I did use correct order of operations there. I did the exponential part first. I changed negative 2 squared to a 4, and then I did multiplication. That's how I did the expression, simplified it. One more problem on this video. So this one's kind of a long one. Actually, the test I think has 23 or 24 problems, but I guess we'll wrap it up with number 10. This is number 39 from the same section. says a manufacturer of satellite systems has monthly fixed costs of $32,000 and variable costs of $432 per system. So the fixed costs are $32,000. And he also has a variable cost of $432 per system. And it sells the systems for $592. So that's the sale price. Write a function that models the profit P from the production and sale of X units of the system. Okay. So we've got to come up with a profit function. Well, before you can come up with a profit function, you need a cost function and a revenue function. And it's kind of implied in this problem that the cost function is a linear function. So it's going to be of the form mx plus b. But just remember, your variable cost is always the coefficient of x, and your fixed cost is always your constant. All right? But we also need a revenue function. And the revenue function in this case is just the price that we sell it for times the number of items that are sold. So it's just the sale price times x. So when you do your profit function, it's just the difference of those two functions. Remember, by definition, profit is revenue minus cost. But notice that I'm putting my cost function in parentheses because I'm distributing that negative sign. So let's use a calculator on this last part. And I get 160 for a coefficient of x. So there's your profit function. And then part B says, what is the profit if 600 satellite systems are produced and sold in 1 month? So you just have to plug in 600 for x. So in terms of notation, it would just be P of 600. And I get 64,000. All right. And the very last part, at what rate does the profit grow as the number of units increases? So they're really asking you for the rate of change of a linear function. Remember, that's always just the slope. So the rate of change is $160 per unit. So every time we sell an additional unit, we make an additional profit of $160. That's kind of the idea. So anytime you're asked for the rate of change of a linear function, it's just the coefficient of the slope of the x. It's just the slope. So that's a lot for this video. I'll do some more problems on another video from that same review, but that's about the first half of it.